Okay, good morning, everyone. Welcome to the second webinar in our fall webinar series on insects and wildfire. My name is Carrie Berger, and I'm part of the Northwest Fire Science Consortium team, and I'll be the moderator today. If you have a question or comment, please type those in the chat box on the left side of your screen, and Sarah, our presenter today, will get to your questions towards the end of her presentation. Below the chat box in the notes, you'll find links to our website, to Sarah's publication, and to the final webinar that's coming up on Monday the 23rd. Okay, so well, thanks for joining us today. And this webinar will be recorded and posted to our website. So if you want to share that with your colleagues, that's always great. So without further ado, I'd like to introduce Dr. Sarah Hart from the University of Colorado Boulder. And Sarah, go ahead when you're ready.
Hi, everyone. Thanks for tuning in today. I know it's a busy time of the year. Today I'm going to be talking a little bit about some work that I've done on mountain pine beetle and the effects on wildfire. My talk today is broken into 4 sections. I'm first going to go over some background material and try and synthesize some of the recent literature that's come out about mountain pine beetle and wildfire. I'm then going to move on to some effects of bark beetles on area burn that I've recently published. I'm going to move on after that to some unpublished work on fire severity in bark beetle. And I'll conclude by talking about some management implications. So on to the background. Well, first, bark beetles have affected significant areas across the western U.S. So here we can see a map of the damage attributed to bark beetles from 1997 to 2012 across the western U.S. And in red, you'll see that there's extensive areas affected by the mountain pine beetle. Note that there's also areas that have experienced infestations of spruce beetles and pinyon ips beetles. Now, the mountain pine beetle is a native bark beetle that causes tree mortality as a result of extensive colonization and feeding within the tree's reproductive tissues. We typically have mountain pine beetles living at endemic levels and where they're feeding upon weakened trees. But when we have warm and dry conditions coupled with abundant, large host trees, we can create these large, extensive outbreaks, and that's what's been occurring lately. And so the mountain pine beetle feeds predominantly upon lodgepole pine and ponderosa pine. Coincident with this increase in bark beetle activity across the West, we've also had a large increase in the number of large wildfires. So 2012, 2006, and 2007, we had some pretty big wildfire years across the western U.S. The coincidence of these 2 disturbances has led to a lot of people discussing how mountain pine beetle infestation and these dead trees across large, extensive landscapes might affect subsequent wildfire. And in the disturbance ecology literature, we talk about these in terms of 2 different types of disturbance interactions. First, compound disturbances, where one disturbance may alter an ecosystem's response to a subsequent disturbance. And so this might be a question about how mountain pine beetle outbreak followed by fire affects the forest's ability to regenerate. Or we can talk about linked disturbances, where one disturbance alters the probability or severity of a subsequent disturbance. And that's what I'm going to be talking about today. However, there's lots of literature about compound interactions between mountain pine beetle and wildfire that I can refer you to at the end of the talk. So the predominant way that mountain pine beetle is expected to influence fire is through alterations to the fuels. And the effects of bark beetle-induced tree mortality are expected to change with time since initial infestation. So today I'm going to talk about 3 stages of mountain pine beetle infestation, and these should be viewed as a continuum as opposed to discrete stages. But first, trees become infested by mountain pine beetles, and the tree fades from a green color to red over the course of about a year. This red stage persists. I'm getting a note that the sound went out. Can everyone hear me? Oh, okay, looks like overall most people can hear me, so I'm going to keep going. Thanks for your feedback. Okay, so during the red stage, the needles are fading from this green color to red. That is occurring over about a year, and these needles are persisting on the tree for about 1 to 3 years. And this red stage leads to changes in the foliar moisture and also the chemical composition of the needles that promotes increased flammability. And what this means in terms of fire behavior is that we're anticipating to see amplified crown behavior and torching as a result of this increased flammability of the needles. The needles start to fall off of the tree, and we move to what's called a gray stage, where there's pretty much no needles left in the tree, and the trees look gray. I'm getting that there's a lot of echo. If there's echo, it's probably on your end for some reason. Okay, I'm going to ignore these comments for a little bit and keep going.
Sarah, go ahead. You do sound good. I think when people are having echo issues, it's their equipment on their end. So go ahead.
Okay, I'm going to keep going. So during the gray stage, the trees have very few needles in the canopy, and we're getting less canopy fuel continuity. This stage persists for about 3 to 10 years, and as a result of all the needles and the twigs and some branches falling to the forest floor, we might expect to see amplified forest fuels, but maybe a decreased probability of canopy fire in the gray stage. Then people can talk about the old stage or the silver stage, and these are outbreaks that have occurred decades ago. And during this stage, we start to see an increase in coarse woody debris on the forest floor and kind of an increase of trees regenerating into the forest canopy. So collectively, we expect that there are changes in the fuel profile that occur as trees move from unaffected to the red stage, to the gray stage, and the old stage. And these stages are expected to change fire behavior. But what does this mean in terms of crown fire occurrence and crown fire severity? Well, these ideas about stand level fire behavior models and the expectations from changes in fuels have been translated to what we might expect to see on the landscape. And so here you can see on the x-axis, time since outbreak, where we have those 3 different stages, the red stage, gray stage, and silver stage. And on the y-axis, I have expected fire occurrence, which is just kind of a rough idea for how fire occurrence or the likelihood might change in response to changes in fuels. So we expect that we might see amplified crown fire occurrence during the red stage as a result of those increased flammability of the needles. Then as the needles fall off the tree, we expect that there might be a decreased likelihood of crown fire occurrence due to kind of a lack of fuels in the canopy and a patchier distribution of canopy fuels. As we start to see trees regenerating back into that canopy, we then might expect to see increased crown fire occurrence. However, I want to note that most of the retrospective studies that have looked at observed crown fire occurrence in actual areas that have been affected by mountain pine beetle have had a little bit of a difficulty trying to identify this linkage. So here, each of these points corresponds with a retrospective study that's been done looking at crown fire occurrence in areas affected by mountain pine beetle or other bark beetles such as the spruce beetle. And in general, what you can see is that there tends to not be a large effect of mountain pine beetle or bark beetles on crown fire occurrence. However, most of these studies tend to be of 1 to several fires, and so there's been questions about whether these studies are representative of the effect of bark beetles on crown fire occurrence at large. We'll now take a look at fire severity, and here I'm talking about canopy fire severity. Again, we've got on the x-axis time since outbreak, and on the y-axis expected fire severity. And the expectation is that, again, as trees move to that red stage from being unaffected, that changes in foliar moisture might promote more severe fire during the red stage. Again, I'll look up some of the existing studies and what they suggest. And here you can see that there tends to be a pattern of varied results. So the effects of mountain pine beetle on canopy fire severity appear to either not be that strong or be convoluted by some of the confounding factors. So this kind of raises the question, why is there a disagreement between fire behavior model expectations and observations? What we've just seen tends to show that our retrospective observational studies of the effects of mountain pine beetle on wildfire severity and occurrence don't kind of line up with our stand level fire behavior model expectations. And I would argue that there's a number of factors that drive this pattern. First, pre-outbreak forest structure and fuels are highly variable, and it's difficult to control for that in our retrospective studies. And secondarily, most stand fire level behavior models make the assumption that all of the fuels are homogeneous, whereas we know that this might not actually be the case. Second, outbreak stage is heterogeneous. This means that it can be difficult to tell how severe an infestation is, and the severity of the infestation might affect subsequent wildfire. Again, this is a problem for both retrospective studies and for stand-level fire behavior models that assume homogeneity of the fuels. Outbreaks also occur in topographically complex landscapes. So whereas stand-level fire behavior models are kind of ruling out topography, when we look at the effects of wildfire or the effects of bark beetle on wildfire in these retrospective landscape scale studies, we have to deal with topography. And also, I want to point out that fire weather is highly variable. And so when we're looking for retrospective effects, sometimes the high gust speeds and low relative humidities that may characterize different periods of burning can affect the fire patterns that we see. So this brings us to how I went about looking for an effect of bark beetles on area burned. Specifically, I was interested in this question: does bark beetle infestation affect area burned at a broad spatial extent? And this is work that was recently published in PNAS with my co-authors Tanya Schoenagel, Tom Veblen, and Teresa Chapman. And the question was really to get at, is there this emergent effect of mountain pine beetle on subsequent area burned at this kind of broad spatial scale? And again, to remind you of our expectation for our fire behavior models, we expected that we might see increased crown fire occurrence during the red stage, followed by decrease in the gray stage. The study area is the entire western US, and so we really were trying to find this emergent effect. Is there more fire burning where we had mountain pine beetle infestation? So we collected data for the time period from 2000 to 2013 on fire area and mountain pine beetle from available geospatial data sets. And we did some spatial analyses. So we gathered mountain pine beetle infestation data from U.S. Forest Service aerial detection surveys. We took all of this data and converted it to a raster of about 990 by 990 meters. And the reason for this kind of coarse spatial scale is that this tends to be the scale where aerial detection survey data is reliable for actually detecting the occurrence of mountain pine beetle infestation. We took all these maps of where mountain pine beetle infestation was occurring across the landscape and kind of converted it to an index to say whether infestation was recent or in that red stage, which would be 2 years prior to fire, or whether it was in the gray stage and had been infested long before fire. We cross-validated these maps of aerial detection survey with maps of mountain pine beetle hosts. And here I took data sets on existing vegetation type from landfire, GAP, and another data set made from AVHRR data to get kind of a composite for where mountain pine beetle hosts were across the western US. And then we kind of overlaid that with maps of the burned area, which were taken from the Monitoring Trends in Burn Severity project. And together, all of these give us time series for where we had mountain pine beetle infestation occurring in mountain pine beetle hosts that overlapped with fire area. So first, let's talk about the trends we saw in these large geospatial data sets. So across the western US, we saw increases in the area affected by mountain pine beetle in lodgepole, ponderosa and mixed lodgepole pine, and ponderosa pine. This is consistent with kind of our expectation. There's been a dramatic increase in the area affected by mountain pine beetle. If we looked at the area that burned in our mountain pine beetle hosts, those lodgepole cover types, those ponderosa and lodgepole cover types combined, and the ponderosa separately, we see that there have been some years of dramatic area burned, but there hasn't been a steep increase in the cumulative area, or in the area burned, that's occurred in response to this cumulative increase in mountain pine beetle. So already the fact that we're not seeing this dramatic increase in area burned in response to increased mountain pine beetle infestation kind of suggests that perhaps these two aren't that tightly coupled. So again, here are the maps side by side. You can see we've got that time on the x-axis, and then the first graph is showing you the area of mountain pine beetle infestation with that clear increase in the area that's been infested. And then if we look at area burned, there doesn't appear to be that dramatic of an increase. To kind of quantify the effect of mountain pine beetle infestation on subsequent fire area, we did some spatial overlay analyses, where basically we took the area that's been infested by mountain pine beetle in the red stage, the gray stage, or that unaffected stage. Those are represented by red, gray, and green on this little diagram here. We overlaid it with fire area. And this basically generates an observed frequency table where I can say how much area burned in uninfested stands, how much burned in gray stands, and how much burned in red stands. This expected frequency table was then converted to, we also calculated an expected relative frequency table, which is just based on the distribution of mountain pine beetle infestation across the landscape. So we're saying how much red is present on the landscape, how much gray is present on the landscape, and then how much of the forest hasn't been infested. This expected relative frequency table we then converted to an expected area burned based on the total area that burned in the mountain pine beetle host cover type. And again, this generates our expected area burned. And the assumption is here that if mountain pine beetle infestation is independent of fire, that the expected area burned should roughly equal the observed area burned. So we'll take a look at some of the results. And on the x-axis, I have the stage of infestation. So we have those uninfested pixels, red stage mountain pine beetle infestation, and then gray stage mountain pine beetle infestation. And on the y-axis is the area, and that refers to the area that burned. So first we'll take a look at the observed area burned. And I'm showing data right now for 2006, 2007, and 2012 fire years combined. Those were three of the largest fire years that occurred in mountain pine beetle host cover type. And those were selected to kind of get at this kind of broad scale trend. So we can see right away that most of the area that burned during those fire years occurred in forests that were uninfested by mountain pine beetle. Next, I'm going to bring in the expected area burned, and that's that area that's based on the distribution of uninfested red and gray stage mountain pine beetle infestation across the West. And so where the expected and the observed area burns are roughly equal, there's not a huge difference between where burning is occurring. So for not infested red and gray stage mountain pine beetle infestation, there was very little difference between our expected and observed values, less than 1%. So we can say that burning overall was not preferentially occurring in areas infested by mountain pine beetles. And these results didn't really depend on host cover type. So here, this is the same type of graph where stage of infestation is on the x-axis, and on the y-axis is the area burned. And this is just showing lodgepole pine cover types for these combined 2006, 2007, and 2012 years. And again, the expected and observed values are very similar. The values, or the results, also did not depend on the actual fire year. So I've shown another graph here which shows all host cover types that burned in 2012. And again, the difference between observed and expected is relatively small. So although we're seeing differences of 3% in comparison to the actual error that occurs in these large data sets, we said that wasn't very meaningful or significant. So collectively, this paper kind of suggests that the emergent effect of mountain pine beetle infestation on the area burned in years of these extreme fires, such as 2006, 2007, and 2012, appears to be negligible at these broad spatial extents. So while mountain pine beetles may alter fuels, and we've seen that in field data, and it may end up altering fire behavior, at this broad spatial scale, we don't actually see increased burning occurring in areas where there's mountain pine beetle infestation. That brings me to my next question. How does mountain pine beetle infestation affect fire severity? So are we actually seeing different effects of fire in areas infested by mountain pine beetles? And the question that I was specifically interested in here is, does red stage mountain pine beetle infestation affect fire severity? Again, to bring things back to the beginning, the expectation is that during this red stage, when we have decreased canopy foliar moisture and changes in the chemical composition of the needles that promote flammability, that we might see increased fire severity. So again, to kind of look at this question, I selected just fires that burned in 2012 that had mountain pine beetle in them prior to that fire year. And I actually ended up selecting just 7 case study fires because the data processing is a little more specific. And I'm sorry those names are showing up a little funky right now. Made on a Mac. But we've got 7 fires: the High Park fire in Colorado, the Porcupine, the Mustang, the Halstead, and the McGuire in Idaho, Waterfalls 2 and Pole Creek in Oregon. And I'm going to talk a little bit about some results that come up when you look at how fire severity varied in relation to mountain pine beetle infestation in these fires. And these fires were selected because they were relatively large and had a higher proportion of pre-fire mountain pine beetle outbreak. So fire severity tends to vary with a number of different landscape features, including weather, topography, and fuels, which can make identifying the effect or the driver of fire severity challenging. So to get around kind of how all of these variables interact, I acquired data on topography for each of these 7 fires, and the topography data that I collected included elevation, slope, aspect, the heat load, which is basically just an index talking about how much energy is incident upon a given surface, accounting for the fact that we have different levels of temperature throughout the day. And then also slope position. And slope position here is kind of a relative measure of where in a landscape a given area sits. So we can have upper slopes, lower slopes, valleys, ridgetops, and flat areas. And note that slope position is independent of actual elevation. So we might talk about a ridgetop, which might make you think of a high elevation, but they're actually independent. In addition to topography data, I acquired data on weather. And so the weather variables I was looking at was relative humidity, wind gust speed, max temperature, precipitation, and a standardized precipitation evapotranspiration index is kind of a measure of broad-scale drought. Real quickly, I'm going to talk about how I actually got to fire weather. And so because it's oftentimes difficult to get daily or real-time indices of how the weather conditions that a fire is burning in, I acquired MODIS fire detection data, which displays the actual day of burning for all these points. And you can acquire this, and it tells you basically when a pixel's temperature was hot enough to indicate that it was burning. All of these points were used to create maps that display when an area was actually burning. And in comparison to some of the data sets that fire managers often draw during the course of a fire burning, this is a relatively independent data set where all days can be calculated. And so now I have maps of the actual day of burning for each of these fires. I then collected data from a RAWS station, which would be the closest weather station to these fires, to actually tell me what the mean daily temperature or mean daily wind speed was when each of these pixels was burning. So that gives me the relative humidity, wind gust speed, max temperature, and total daily precipitation for each pixel within a fire. The standardized precipitation evapotranspiration index was acquired at a kind of coarser scale. This displays drought pressure over the aggregated 3 months prior to fire and was calculated using PRISM data. So I told you that landscape drivers of fire severity tend to vary with topography, weather, and fuels. To get data on fuels, I acquired existing vegetation type from the Landfire project, pre-outbreak fuel data, and this is also from the Landfire project. And here I just acquired fuels data based on around the year 2000. So it's kind of accounting for the fact that we haven't had mountain pine beetle infestation in that landscape yet. And then mountain pine beetle infestation data. And while in the previous study I talked about using aerial detection survey data, I really needed to get a finer scale measure of mountain pine beetle infestation for this study. So I acquired high resolution 1 meter aerial imagery. And this is what this type of imagery looks like. It's from the NAPE program. And I used this data to kind of classify where we had red stage mountain pine beetle infestation. And so I created these maps of classified aerial imagery where we had basically uninfested forest, red stage mountain pine beetle, non-forest cover, and shadow. And this type of classification resulted in an overall classification accuracy of about 87%, which is pretty good, or a user's accuracy between 80 and 94% for each of these 4 classes. So this is kind of our index of where mountain pine beetle infestation has occurred on the landscape. And this imagery was collected in 2011, so that we have an idea for how much red stage mountain pine beetle infestation occurred prior to the fire. So we have all of these geospatial data sets on topography, weather, and fuels. And then I asked this question about how these variables ended up affecting fire severity. And the fire severity data I used was, again, from the Monitoring Trends and Burn Severity project. And it's the relative differenced normalized burn ratio, or RDNBR. And this is an index of how severe a fire was that's collected at a 30 by 30 meter scale based off of Landsat imagery. And so to try and relate these predictor variables to our response variable, the fire severity, I used a method called classification and regression trees, or CART. And these variables were all put into a number of these different classification trees to try and get at which variables were predicting fire severity across all of these fires combined. And so in contrast to something like linear regression, which looks for a linear relationship between your predictor variable and your response variable, CART actually works by partitioning your data into separate groups that can continuously, that basically doesn't rely on independent variables or have any effect of autocorrelation. It's kind of independent of that, so it's useful for some of these broad-scale landscape analyses where we have nonlinear relationships, interactions between variables, and multicollinearity. So these number of tons and tons of regression trees were basically averaged to come up with an idea for which variables end up predicting fire severity the best across these landscapes. And again, this is for all 7 of those fires combined. How do we know what drives fire severity? And so what I ended up doing was calculating this variable importance measure, which tells us which variable is the most important in predicting RDMBR. And you can see that on the x-axis, whereas on the y-axis, I have all of those predictor variables. And it ended up being that slope position was the most important predictor of fire severity across all of these 7 fires combined. We then saw temperature and elevation variables driving more of the explanatory power of the model. Mountain pine beetle infestation was not a strong predictor of fire severity. However, there were significant effects of mountain pine beetle that occurred in different subsets of the data. So it's not to say that it can't affect fire severity, but just when we're talking about how we should expect fire severity to occur in a landscape, it ends up being things like topography and fire weather that drive our patterns a little more predominantly. However, it ends up being that fire severity, this RDMBR metric, is difficult to explain from topography, vegetation, and weather alone at this core scale. So the explanatory power of my model was only about 45% of the variability in fire severity could be explained by these variables combined, which suggests that there's a lot of other drivers of fire severity that weren't captured by my model. But collectively, I think that this kind of suggests that fire severity was driven primarily by fire weather and topography and not mountain pine beetle infestation, although I think there's still a lot that can be done to help improve our understanding of the effects of fire topography or fire severity, topography, weather, and fuels and how they interact. Okay, so now I'm going to move on to the last part of my talk, which is just a little bit about the management implications of this work. So I've just told you that I didn't find a large effect of fire area, or a large effect of mountain pine beetle infestation on fire area across the West. And what I think that this means is that severe wildfire is not a necessary consequence of bark beetle outbreak. So collectively, I think that we should start thinking about whether we're actually going to see increased fire in mountain pine beetle forests is dependent upon a number of other factors that drive fire area. And maybe there's not an increased risk as a result of bark beetle outbreak. So I think what this means is that policy discussions where we're talking about wildfire and bark beetle should really focus on the underlying drivers to both of these disturbances rather than the actual synergism between the two disturbances. So we know that drought is promoting broad-scale fire across the West, and we know that it also ends up promoting bark beetle infestation. If we want to start talking about improving the resilience and resistance of our forests to global change, I think it's more important that we start thinking about how climate change and drought may end up affecting fires than really planning for a synergistic effect of mountain pine beetle infestation, which doesn't appear to affect fire area at a broad scale or have a large impact on driving fire severity in these kind of high elevation forests that typically experience extreme fire weather. However, I do want to say that although there isn't great evidence that bark beetle outbreaks may influence fire area or fire severity. Bark beetle outbreaks may influence other measures of fire behavior, such as fire intensity and crowning behavior. And these probably are important for firefighters. There's been lots of reports of increased spotting in areas where there's mountain pine beetle infestation. So we might need to start thinking about how we actually fight fires in these landscapes. But the emergent effect after the fire has occurred on vegetation just probably isn't where we should be focusing our emphasis. If we want to talk about how to actually deal with mountain pine beetle infestation that's present on the landscape, I think that we should probably talk about tree removal to reduce tree fall risks, which clearly can impact people. So tree falls near homes, recreational sites, and communication lines is clearly justified, and that might be a way to start targeting how to deal with massive landscapes that have mountain pine beetle infestation, rather than trying to treat these landscapes for subsequent fire. So that's all I've got, and I just want to say thanks to the people who funded this work, notably the Wilberforce Foundation, and also I would like to thank my lab mates at the University of Colorado for insightful comments and conversations about this throughout the past couple of years. And with that, I will handle any questions.
Great. I just want to say thanks for that presentation, Sarah. That was really interesting. Yeah, like Sarah said, let's open this up to questions. And it looks like, Sarah, you have a question from Gina. So go ahead.
Yeah, so Gina wants to know, were the fires that were included in my case studies from forests with similar historic fire regimes, stand replacing or mixed severity? So I selected fires that were burning in mountain pine beetle host cover types, and then I just looked at fire severity within those mountain pine beetle host cover types, and then used as a predictor of fire severity the actual vegetation type to try and control for the fact that there might be different effects that correspond with different forest types. Does that answer your question, Gina? Yeah, so the fires do encompass a mix of different vegetation types. So there can be ponderosa pine, mixed ponderosa pine, and lodgepole pine in the same forest that burn in that fire. However, yeah, to try and control for that, I use the actual vegetation type, so the forest type, whether it's ponderosa pine or lodgepole pine, as a predictor. I see a lot of people are typing, so I'm sorry if there's some awkward blanks here. So I've got a question from Brian here who wants to know, what was the direction of the effect from mountain pine beetle on fire severity that you detected? Yeah, so the direction varied a lot given different conditions. So the way that classification and regression trees works is it tends to partition the data into lots of binary different sets and then look to increase the explanatory power based on how it's dividing these splits. And so largely there was increased fire severity in this red stage. However, it wasn't always consistent. And again, when I plotted just red stage of mountain pine beetle infestation versus RDMBR, there wasn't a significant trend, which suggests that it's not a large effect, but in certain conditions, there may be a slight effect.
Sarah, while folks are typing their questions in, I just want to again point people to the notes section of our, I've given our link to our website where the recorded version of this webinar will be posted, as well as Sarah's papers that she noted here in her webinar, the paper that you just published in PNAS. So go ahead and visit our website to get dive in deeper into Sarah's work.
So I've got a question from Justin. Do you think your findings about area burn and fire severity would be different in normal fire years versus extreme fire years? And so I think that's getting at the fact that for that analysis that I did in PNAS, we only looked at fires in 2006, 2007, and 2012. I don't think that there would be a large difference, and part of the reason why I think that you might see the same trend in moderate years is when you look at those trends in fire area that have occurred from 2000 to 2013 and relate them to actual trends in mountain pine beetle infestation, there's just not that large increase in any of those years. So I have a feeling that you wouldn't see a large effect, but I do think that that's still an area of active research.
Okay, we still have about 20 minutes left, so if anybody has, I see other people are typing, so we'll just hold on here for their questions.
Garrett wants to know if I have specific results for the Pole Creek fire. I do indeed. I ran these analyses where I looked at fire severity in relation to mountain pine beetle infestation for each fire individually as well as aggregated, and it tended to be the same results where topographic position index tended to drive fire severity. Sometimes elevation played a larger role, but this was in part because when you look at elevation for an individual fire, it has a greater relationship to kind of forest composition and fuels than you would when you compared fires from Oregon and fires from Colorado, where the elevation ranges are very different. So Pole Creek, again, I saw a large effect of slope position and not a large effect of mountain pine beetle infestation. And I'm happy to chat more about that later with you, Garrett, if you want. I've got a question from Eric here who wants to know, do you think that you would see a similar pattern in other pine tree stands affected by a different species of Dendroctonus, i.e. western and southern pine beetle? That's a great question. I'm going to first handle the question about whether we'd see an increase in fire area in other species. And I think it in part depends on the fire regime that occurs in that landscape. And so I can talk a little bit about outbreaks of spruce beetles, which also tend to occur in forests that experience relatively infrequent fire, and it tends to have fire when we have periods of drought. And I think in those forests we would see a similar trend. I think where it's a little less well understood might be some of the kind of forests that aren't experiencing these high severity infrequent fire regimes. Gina wants to know if I'm going to look at silver forests next. Is there a lot of salvage logging of these red silver forests that is justified by reducing future fire risks? Yeah, so I have not looked at silver forests yet, in part because there's not a lot of great data for that across the entire western US, although Garrett's done some good work on that. And in terms of the salvage logging question, I specifically tried to remove any other disturbances from my study area, mask them out when I was looking at the effects of future fire risk. And I think in order to get at that silver question, you'd really have to do a little bit more work on that stage that I just haven't done. So I've got a question from Joey here. He wants to know if there are any scenarios in which fire effects of pine beetle kill might be observed, and whether I can maybe anecdotally say anything about this from the data. Yeah, I think that that's an area that really needs more research, because there are clearly alterations to the fuel complexes that occur with mountain pine beetle infestation, and it's becoming more clear that this may alter some parts of fire behavior, but I think actually linking those mechanisms from these kind of fine scale changes in fuels up to these kind of larger scale landscape level patterns is missing. So I'm hoping that that will be one of the things that some of these large data sets, such as the Monitoring Trends and Burn Severity Project, can give you, will be an idea for how and when this varies across a landscape to really pick down to when we might see these conditions affect fire severity. But I think the take-home point is really just that in most conditions, it's not going to matter. Okay, Brian wants to know, for the minor effects that I saw on mountain pine beetle on fire severity, are they biologically meaningful? In other words, do they qualitatively change fire severity? So I think overall, no. I think overall, the factors that are driving fire severity across this landscape are not these small changes that are occurring in fuels. When we have these kind of really hot, dry conditions, there's enough fuels present on the landscape to create severe fire. And I would suggest that that is the real take-home message. But I do think that at some point there should be some observable effect of mountain pine beetle. It just is going to be in a very, very small proportion of the cases, such that it's not an emergent driver of fire severity that we should really be worrying about. It looks like the flurry of questions is starting to die down, but if anyone has any last questions, get them in now, or if you want to converse on this over email, I'm happy to do that too. My email is listed down there at the bottom.
Well, as people are getting their final questions into, I just want to take this opportunity to say thanks you all, the audience, for joining us today. We know that this is an extremely busy time for everybody, so it's fantastic that you all could take some time out of your schedules. And also a huge thank you to Sarah Hart for presenting this really great research to us today. So thanks a lot for that, Sarah.
Yeah, thanks for having me. And for those of you going to AFE, I know there's a lot of other great meetings and discussions about mountain pine beetle and fire. I think Brian Harvey is giving one, and I think Jeff Hickey is talking about mountain pine beetle and fire, and I think Garrett's got a talk too. So if you're interested in this topic, make sure to check out their talks. They're doing some great work as well.
Fantastic. And so after that AFE conference, tune in again on that Monday, the 23rd. We'll have our final webinar in this webinar series on insects and wildfire. We'll be presenting on fuels patterns and a fire following mountain pine beetle mortality in the Climax lodgepole pine forests of southern central Oregon. So, okay, everybody, thanks for joining in today, and we'll hopefully see you all back here on Monday, the 23rd.
Bye, everyone. Thanks again for tuning in.